Chapter 6, the Periodic Table. By 1860, 60 elements had been discovered and their atomic masses calculated. They grouped the elements that had similar properties. Copper, silver, and gold were the coinage metals because they were non-reactive and were used in coins. Lithium, sodium, and potassium were the alkali metals because they reacted with water to form alkali compounds. Alkali compounds are bases. Chlorine, bromine, and iodine were the halogens because they reacted with metals to form salts. Halo means salt, and gen means to generate. They began organizing elements to show these similarities and used atomic mass as their organizer. A German chemist named Johann Duberreiner lived from 1780 to 1849. In 1829, he grouped 3 elements with similar properties, which he called triads, and the groups are listed. Calcium, strontium, and barium were grouped, chlorine, bromine, and iodine, lithium, sodium, and potassium, sulfur, selenium, and tellurium. The middle element of the triad was an average of the other 2 atomic masses. Other properties also followed similar trends like density, melting point, and boiling point. Triads were useful because they revealed patterns of physical properties. But the weaknesses of triad classification is 1, a large number of similar elements could not be grouped into triads. For example, iron, manganese, and nickel are similar but could not be placed in triads. And also, 2, it was possible that quite dissimilar elements could be grouped into triads, mainly on their average atomic mass being the mass of the middle atom. Now, here are Duberreiner's triads on the current periodic table. You'll notice that all of the groups are in vertical columns. And we learned before that vertical columns are called groups or families because they have similar properties. Now, here are some examples of Duberreiner's atomic mass calculations. If you take calcium at 40, barium at 137, their average is 88.5. Well, strontium comes in at 87.6, pretty close. Chlorine, 35.5. Iodine, 127, the average is 81.3. Bromine comes at 79.9. Sulfur, 32. Tellurium, 127, the average is 79.8. And selenium is 79.2, pretty close. Then, from 1837 to 1898, an English chemist named John Newlands was the first to arrange elements according to atomic mass. So around 1863, he came up with the law of octaves, where the properties of elements seemed to change on every 8th element. The noble gases were not yet known. The weaknesses of his triads is it could only be applied up to element 20, which is calcium. Newly discovered elements could not fit into the octave structure. And number 3, the feature of resemblance of the 8th element when arranged in increasing atomic mass was not successful with heavier elements. As I said before, it was only applied best up to element number 20. Now, here are his octaves. If you look at Newland's periodic table, lithium, beryllium, boron, as it goes left to right, notice they are every 7, and then the 8th one is a repeater. But you'll also notice that in some of his columns, he has more than one element. That couldn't work. As I said, it only went up to calcium, and yet they did not know the noble gases, so there are elements missing. Here's the game changer. The father of the modern periodic table, Dmitri Mendeleev, lived from 1834 to 1907, and he was the first to group elements with similar properties in columns. And he arranged the elements by increasing atomic masses. And what makes him different is he predicted properties of missing elements, and he actually left blanks in his table. He predicted an element that he called Eka aluminum, which later was named gallium. And the properties that he predicted were almost perfect. He made up the term called periodicity, where regular repeating patterns of variations of properties will then increase with atomic number and also with their position on the periodic table. Here is his periodic table. Now it's in Russian. But if you look where I have the red circle, he has zinc, and then he has arsenic, and then he has two elements which he assumed had the masses of 68 and 70. And as I said before, when they actually discovered the elements, they almost matched his math exactly. Like I said, 68, 70 left them blank, and he predicted the properties of gallium and germanium almost to a T. Henry Moseley, who was a British chemist, lived from 1887 to 1915. In 1913, he found atomic numbers of elements by measuring wavelengths of X-rays given off by specific elements. So he was the first one to actually change the periodic table from increasing atomic mass to increasing atomic number. And he also formulated the periodic law, which says there's a repeating pattern in chemical and physical properties of elements when they're arranged by increasing atomic numbers. The current periodic table. There are 7 horizontal rows. Those are the periods. The properties of elements in a period change as you go left to right. The groups are the 18 vertical columns. They're also called families. And the elements in those columns will have similar properties. Valence electrons are the electrons in the outermost electron of an atom. The number of valence electron increases from left to right across a period from 1 to a maximum of 8. The number of valence electrons is identical for all elements in a vertical group. Add this to yours. Valence electrons are the outermost s and p electrons. So if you're looking at an electron configuration, only the listed s and p electrons in a valence configuration will be the valence electrons, because s is 2, p is 6, therefore the maximum is 8. What are the 3 general classes of elements? They are metals, which you see here in yellow, the metalloids, which are an olive green, and the nonmetals, which are a blue-green. Across a period from left to right, the properties of elements become less metallic and more non-metallic. And as you can see, as you go left to right, you go from metallic to metalloid to non-metal. The metals make up about 80% of all the elements. All of them that you see here are metals, the ones that are shaded in. The only ones that are not shaded in are hydrogen, the nonmetals, and the metalloids on the staircase. What does it mean that metals have sheen? Well, sheen is, they say it's got high luster or it's shiny. All metals are solid except the one you see in the upper right-hand corner, mercury. What is meant for a metal to be ductile? That means it can be formed into wires. They call that ductility. And what is it meant for them to be malleable? That means you can hammer them into sheets or hit them with a mallet. So that's where the term malleable comes from. And when you do hit them, they do not break. Now, the nonmetals are those to the right of the red staircase and hydrogen. What part of the periodic table are nonmetals found? The right side of the staircase, except hydrogen, which is on the left. Most nonmetals are gases at room temperature, where we just said that most metals are solids at room temperature. There are 5 nonmetallic solids are carbon, iodine, phosphorus, sulfur, and selenium. Bromine is the only liquid metal at room temperature. Just like mercury is the only liquid metal, bromine is the only liquid nonmetal. The properties of nonmetals are usually opposite of those of metals. Most nonmetals are poor conductors of heat and electricity, where metals are opposite. They're usually very good conductors of heat and electricity. Nonmetals tend to be brittle. What does it mean if something's brittle? That means they shatter when they're hit with a hammer, unlike a metal, which is malleable and just changes shape when it's hit with a hammer. There's a heavy staircase line that separates the metals from the nonmetals. These are the metalloids. If you look at the red staircase that is drawn, that is the separator between the metals and the nonmetals, and those, boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, are the metalloids. Now, what makes a metalloid a metalloid? Metalloids are elements that have properties of both metals and nonmetals. The element silicon is used in computer chips, and silicon dioxide is used in glass.
Our furnace, also called the beehive, will cook 12 colors at one time. The ceramic fire clay pots are also known as crucibles. Each crucible can hold approximately 1,400 pounds of chemicals, and again there are 12 crucibles in that furnace.
We actually have a couple of different things that are going to be going on.
Each sheet is carefully ladled and brought to the mixing table. The workers will deposit that glass onto the mixing table and back away. The table man carefully mixes his glass with a 2-pronged fork. Once the glass is blended to his specifications, he picks that molten mixture up and feeds it between 2 rollers, sort of like 2 rolling pins that work together, that will mash that glass flat to 1/8 of an inch thick. The ladles that these employees use are very heavy. This is no job for a lad. Empty, they weigh 20 to 50 pounds. Full, they can double that in weight. Tableman will ring his bell approximately every minute and a half to let the ladlers know it is time for that next sheet of glass. The heavy steel mixing table is cooled by water inside. As the first step to that cooling process, the 2 rollers are hollowed and they are air-cooled inside. Once the glass is rolled out into that 1/8 inch thickness, it changes its traveling direction where it enters the annealing layer for the final cooling process.
Now, when you look at your periodic table, you will see some of the elements are the symbols in red. Those are your gases. The 2 liquids, mercury and bromine, their symbols are in blue to tell you that are liquid at room temperature, and the ones on the periodic table that look outlined are the synthetic ones, the ones that have only been created in a lab. They don't exist naturally on Earth. They've actually created them. When you look at it, all of the others that are in white, those are all solids that are naturally occurring. Classifying elements. Electron configurations in groups. As we said in the last section, valence electrons are the outermost s and p electrons. If you know an electron configuration, you can calculate the valence electrons. So in Chapter 5, we did electron configurations of atoms and ions. Now we're going to start looking at them as valence electrons so we can then figure out how they're going to bond in later chapters. So nitrogen is atomic number 7. The electron configuration is a helium core, 2s2, 2p3. The 2 s's and the 3 p's make up 5 valence electrons. So group 7, or I should say element number 7, has 5 valence electrons because its outermost electrons are the 2, level 2, and there are 5 total. If I look at antimony, which is number 51, it's in the same column as nitrogen. And its electron configuration is krypton 4d10, 5s2, 5p3. Well, notice the 5s are the outermost level, and the s's and the p's, there's 2 and 3, just like there was in nitrogen. So there are 5 valence electrons. D electrons are not valence electrons, and how can you tell that? Because all valence electrons will have the same energy level, and they have the highest energy level. So 5 is the highest number, so the 4 Ds are not in the 5th energy level. Same thing with copper. I look up copper, oh look, it's one of the exceptions, and it's 3d10, 4s1. So those 3d10 electrons are not valent, only the 1 4s electron. Technetium, 4d5, 5s2. Because 5 is the highest level and only S and P, the 5 that are there are not valence electrons. Chlorine, 3s2, 3p5 is the outermost energy level, 2 plus 5 is 7. Now, an easy way to do this, if you're just trying to figure out electron configurations, if you look at the periodic table, you don't even really need to look at the electron configuration. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Groups 3 through 12 we'll get to in a moment. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 8, group 8, you'll notice, which is group 18, has 2 for helium, but 8 for the rest, because remember, there are no p electrons in the first energy level, so the maximum can be 2. Now, groups 3 through 12 are going to be the s electrons. They are found in the d sublevel, but they only have outermost s electrons as their valence electrons. On this table, I'm going to give you a tabular explanation of what I just said. Group 1, which is also called 1A, I have examples sodium and cesium. They both end in S1. That's 1 valence electron. Group 2, or 2A, has S2, so they have 2 valence electrons. Groups 3 through 12, I put a double star there. It could be 0, 1, or 2. If you look at the example copper, it has 4s1, so that's 1. Technetium is 5s2, that's 2. There's one element in the D sublevel, which is groups 3 through 12, that has 0. See if you can find it. Group 13, which is also called 3A, is aluminum and indium, but notice they're S2P1, so the 2 S's and the 1 P makes 3. 14, they're all S2P2s, so 2 plus 2 is 4. 15, they're all S2P3s. 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7, and for group 18, helium is a 2 because there are no P's in the 1s sublevel, and neon, which is 3s2, 3p6, along with argon and krypton and xenon and radon, all have 8 because they're all s2p6s. The alkali metals. The group 1 metals are alkali metals. They react strongly with water to form alkalis. Now, when we were talking about Dobereiner, we were saying that he had lithium, sodium, and potassium in a triad. They're also, if you look on the periodic table, the first 3 alkali metals. There are others that were discovered after his lifespan.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
Quite an explosion there. Alkaline earth metals are the group 2 metals, beryllium, magnesium, down to radium. They get their name because their oxides give alkaline solutions. So calcium oxide dissolved in water gives an alkaline solution of calcium hydroxide. Same thing with magnesium oxide. When you do that, their oxides will turn into alkaline solutions. These oxides also melt at a very high temperature as they remain solids. That's why they were called earths, because once they're oxidized, they don't burn in fires. So basically at that point, they would be ash. Here we have magnesium, calcium, strontium, and barium. Notice as you go left to right here, which is top to bottom on the periodic table, they get more and more reactive. Now, some people look at the second one, calcium, and they say, but that one looks like it's more reactive. Actually, what's going on in there is there's 2 reactions occurring, and that's why it looks more reactive. Because with magnesium, strontium, and barium, as you go top to bottom on the periodic table, they are giving off hydrogen and forming hydroxides, but the calcium that's in there is also reacting with carbon dioxide to form chalk, calcium carbonate. Group 17, the halogens. The group 17 elements are called the halogen. The term halogen originates from the adaptations of the Greek roots hals, which means sea, or halos, which means salt, and gen, which means to generate, referring that these elements will produce a salt in a reaction with a metal.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish-yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid, and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of the pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides: AlF3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
Now, group 18 are the noble gases.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Now, The group 18 elements are called the noble gases. That is translated from the German noun Edelgas, which first used to indicate extremely low level of reactivity. They were also called inert gases, which means not reactive. The name makes an analogy to the term noble gases such as gold, which were associated with wealth and nobility and also with low reactivity. Now you will see that helium has 2 valence electrons, but all the rest, because they're S2P6s, all have 8 valence electrons. And that is what makes them so inert or unreactive, is the fact that they have full shells, which makes them stable, which makes it to the fact that they do not want to react. They're already fulfilled. Now, a general setup of the periodic table, groups 1 and 2, which are there in red and gray, and groups 13 through 18, which are the P's and the 1s2 for helium, are called representative elements. So the ones that end in S or end in P are representative elements. The others, when we're talking about groups 3 through 12, are the transition metals, and the inner transition metals are ones that would be inside the transition metals, and those are listed at the bottom. Now on this one, you'll notice that I have lanthanum and actinium in green because they're really not inner transition metals. The row of metals is called the lanthanide series, but lanthanum is really a D element, so it's a transition metal. Same thing with actinium. So if you do count mine, you will see that it is the yellows are the inner transition and the greens are the transition metals.